this computer. So, okay, didn't start recording. I'm just gonna let people who are watching the video and were not in attendance to see what I did. Here.
I want to ask.
Let me recap this before we. Yeah, let me recap. So we talked about this problem here. That's in Moodle. That's not it. I think it was over here. So we had this for homework this week, and we decided that we had to count for each interval. You have to count how many observations fall within this range, and you have to do that all the way down. And you can use a ruler that can help you. And then you'll identify that B is the answer. Okay, that's how you do that one. And where, just to clarify, so that this is really the variable that's on this axis in the time plot, but it's here where you're counting how many fall in each of the intervals, in this case for time spent studying. And then we solved for the third quartile. This is the second problem I had for homework. And we accumulated how many observations there were. Then we use the number of observations, n equals 31, to find the median. Once we found the median, we divided the data in two and found the median of the second half to get the third quartile. And we have the answer is E. Oh, and I didn't say what the answer was on the other one. The answer was, on this one, was B. All right. So I will take your question now.
I had a question. I don't know if Paula also
Sorry?
has a question.
Go ahead, Inaru.
Yeah. So in the second problem that I saw, I think it was Cristina that put like the first quartile, the second one, and then we did the third together. I just wanted to know if, like, for the first one, we also look for the median in the first half, and then it's that number, or how we get like the other two.
Say it again.
Okay, so we had to look for the third quartile, right?
Yeah.
But if we were looking for the first one, it would be the median in the first half.
Yeah.
And then to get the second one, how would that be?
Well, the second one is the median. So we already have that.
Okay.
Yeah. So that's Q2.
Okay, just wanted to confirm that.
Yes, this is Q2. And if you needed a Q1, you would also count 8, but from the top. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8,000.
And if it wasn't like how do you say, like if it was 30 flat, do we have an example like that of how we would get?
If there's 30, not 31,
Exactly.
you have to average the two in the middle.
Okay.
We did it last week. But yeah, if you have an even number, then you don't have an absolute center. So you have to average the two middle observations, and the median is in the bit in between. And then you exclude it. You just use the data, that first half and the second half, you divide them. Right? Is that okay? Does it make sense?
Yeah. Just wanted to like confirm because that's what I thought, but wasn't sure.
Okay, good. I'm just looking at the questions about the questions in the photo. Sorry, I'm yawning. On a question 13, I selected two of the options. So the questions should be randomized. Everyone sees them in a different order. But if you describe the question, I can figure out which one you were looking at. So I selected two of the options I thought were the correct answer, but it keeps marking my answer as incorrect. What would be the first class interval for the frequency histogram? And my answer was 5 to 6, which is marked as incorrect. So I went ahead and selected my second option, 5.2 lessons, and it was also marked incorrect. Could you please explain? So again, I have to go into Connect and see. All right, so this happened last class where you asked me Connect problems. And I need to go into the system to look at it. So what I'm going to do is at the end of this video, if we finish by 11:30, we have time, I'll do it. I'll do the two Connect problems. This one and another one that's outstanding from last week. And everybody can go and I'll just make the video of it. So that's what I'll do. I'll do the Connect answers at the end because I'm going to be taken into a rabbit hole and spend some time there. So I'll do that at the end. Okay. So if you're not here, you can just watch it. If you have to leave by 11:30, I'll do it after 11:30 and I'll leave it at the end of the video. You can come back and watch it for the answer. Is that all right, Sally? Is she here? And then let's see.
Yes,
Okay. Sorry about
thank
that.
you.
It's just because I do want to answer it. And then Melba said something. Let's see what Melba said. She answered it. Oh, okay. She's also confused. Okay.
Yes.
Okay. All right. So I'll look at that. And then there's the one from last week too that I didn't get to, but I just have to look at the terminology they're using because if there's confusion, you guys are probably right. Just because I noticed before last year there was some confusion about the Connect exercises. If so many students are confused, you're probably right, but I'll look into it. To confirm. All right, let's see. There was, I think, something in the photo over here. Yeah, Melba. Yeah, this one.
Yeah.
I just don't think the options are clear at all. And the point here for block design, in a block design, you split into a block of women and men or blocks that are going to react differently to the treatment in a systematic way. So maybe different is the right answer. It's just not very clear. One word doesn't just do it. Is different the right answer, Melba? Did you try that one?
I didn't, but I found in the textbook that the sentence says it was the same.
Okay.
So I got confused.
Okay, I'll look at the book too and see how they wrote that.
Okay.
Yeah. Yeah, because there are different, like when it's a blog, you're doing with women that are getting all the units, I mean all the treatments, and then men are getting all the treatments. So they're different, right? But it's not very clear there.
Mhm.
It's just one word different, like different in what way? Like they're still people, they're still humans, but different by block. It should say something like different by their block characteristic or different. I think it's a poorly worded question, but I'll look back at the textbook too and see to clarify. There might be some words in there that are misleading. And I'll check if that different works.
Carla says she tried different and the same, and both
Okay, so
answers
then
were
it's
marked
just like an
incorrect.
error in the
Mhm.
thing. The
Yes.
important thing, I'll try and delete the question because it's not a good question. But to
Okay.
tell you, well, let me see what they say. Let me see what they pick as their answer. Randomly selected, no. Representative, maybe that's the answer then. It's still the bad wording. So delete the question about blocks. And that's in assignment 1. and I'll see if I can do it. And then, I think I can after like it closes. Oh, you have till the 24, right? It's still open?
Yeah, it's still open.
Okay. Yeah, so I'll see. The connect problem shouldn't be too hard. It's just for me to get some extra points for you and have you review, your knowledge, not meant to be as challenging as some of the material I have on the Moodle. So this is about, okay. Yeah, so I'll put that at the end of the video. All
Okay,
right,
thank
so
you.
then, great. All right, so any other questions about graphing and descriptive statistics? Any other thoughts or questions or something that came to mind that you'd like to know about? Put it in the chat. Anything outstanding that you just don't get? Jordan has a question about gauges. Measurement. Okay, I'll look at the gauges problem too. Yeah, it might be representative because blocks are like stratifications, but we reserve certain words for certain concepts, and that would be bad if they did that. But as I think it was Inato was saying that she picked the same because it's in the book, or Melva. Anyway, so I'll look at all that.
Hello.
Yeah, Melva. Okay, good. Okay, so if you have no comments about graphing and descriptive statistics, we can move on. Did you like this unit? Did you like working with the numbers? This is very tangible, you can you're interpreting graphs, you're making calculations. Okay, good. Very tangible. When I was a student, I started my degree in mathematics and I moved into statistics because I found mathematics was very intangible for me. Everything was very theoretical, and I really like statistics because I could do things with the numbers. And so
But isn't that the same thing with math? Like there's a lot of parts of math that are applicable. I guess it's just a human
I,
problem that we don't do it.
no, I was in like a theoretical math program. It was just too much. It was too removed. It's important. I think mathematicians are important, and I'm not dismissing that. I just couldn't grasp what was going on as much as with numbers. So that's why I ended up here. But it depends, what school you go to, who your professors are, that make it come to life. And the statistics professors were better for me. All right, so okay, so I will suppress those exercises. So we're in the normal distribution. So for the normal distribution, you should download these notes and work through them. I have the videos there for most of the data. There's just some places that I don't have the videos. So I'll run through a few things here.
Professor, could you explain in the first page
Yeah.
we have sickness, and I tried to this exercise in Excel. I used SKU, but my result was a little different. And I want to know if I did right or not. My answer was negative 0.31499, but the answer in the document is negative 0.23421. If you could perform this exercise in Excel.
Yeah, so Excel might be using a different, I don't know, estimate approach, or maybe you're picking the wrong one. So you did this in Excel and you chose skewness. We could
Yes,
do the
I
same thing
select
power by-
skewness and then I perform also with skew point B. I think this population, but
Okay, so okay,
mhm.
let me see. So let's go to Excel because we're gonna do normal distribution in Excel. I think what I meant, I believe what I meant by saying use Excel was to make a table, not to use the Excel function. I think that's what I was referring to here. And so you can make a table again. This is like an average. Remember we talked about seeing a sign, like a sigma sign, and an N on the bottom. It's kind of like an average, but you're not squaring, you're cubing, and then you're dividing by S cubed. Now, whatever this comes from, I'm not going to test you on this. It was just to show another kind of so statistics is about averages and relative measures. This is like an average. It's summing these up. It's summing up some values and averaging them. And the values are cubed for some reason. And then you are standardizing them by dividing by the standard deviation cubed as well, and canceling and making it an index. That's the idea. So it's usually, statistics is like that. I'm not going to test you on this, so don't worry about that. And it's possible, I don't doubt that I use the formula to get this value. So I made like columns like I would for the standard deviation from the mean. And then I cube them, and then I average them, and then I divided by S cubed, which is the standard deviation of the sample. That's how I did that. You didn't do that though, right? You just got the skewness variable out of Excel.
Yes.
All right. So be cautious of using Excel until you know for sure what formula it's using. That's going to be the lesson from this experience you had. So just be sure you're using the right one. You'd have to go and make sure, like, what is, like, let me see online. Let me check skewness in Excel. There's some things, like I mentioned last class, the 5-number summary is a little bit different in different statistical packages. It's not standardized and it's kind of frustrating. So skew, right? You use skew, but I need to know, how do you calculate skewness in Excel? It might be slightly different, but it was a negative. It was a negative that you got.
Yes, negative 0.31499.
So there's different formulas for skewness. Look at this one, 3 mean minus median, standard deviation. Like there's different formulas. I just proposed that one at the time, probably for the textbook that I was using. Let me see. So it was here. And this one was negative. Okay. So don't worry. As the main thing is that it's a negative and that it's close to 0. And that tells you that it's close to, that's the main thing. Okay. So you got a little bit different. Excel might have a different formula than what I put here. But this is like for the textbook, this is the one I was using for the textbook, but Excel might have a slightly different way to do it. There's different ways to do it. So the most important thing is that you got the negative. That's going to tell you it's negative, but the really important thing is that it's close to 0. So you could see that either as slightly left skewed or symmetric. I know this seems like in reality, when you do statistics, it's less exact. And I'm trying to give you examples like that, that here, if I saw you saying it was symmetric, I would be okay with that. And left skewed, I would be okay with that. But it's not a strong left skew. Okay, I'm just going to read Jordan here. You should be studying for the test, Jordan. I always do a little bit of review, but you know, you're responsible to get through everything I have there. And when we do the review, I always add different questions. So with the understanding that you've reviewed everything I have in Moodle, but I will look at any ones that you have problems with. Yeah, so let me look at the schedule, make sure I have time for that, because we're gonna do normal today. And then, oh yeah, we have lots of time. And then next week, regression. You're going to study regression this week. You're going to finish normal distribution and study regression this week. Next week, we're going to do regression. Regression is a very short unit, and we can start studying next week together. We'll do review problems. And then your test is the following week. We'll also meet then, and I can do more problems before the test. And you do have 3 days to complete the test. So presumably you should be done all the material, but you'll have still some time to do some review. Don't leave everything till that weekend. It's going to be a lot. So make sure you do a little bit. Make sure you finish. If you can finish the review of the material by next week, you're on track. Then you can study for the test all week. To study for the test, I have old exams. So there's a regression. Sorry, I always have to scroll through so fast. Those are the regression. It's very small unit. You watch this video for 3 hours. These are just some extra videos if you need assistance for the pages. And that's it. You know, it's very short. And you have a bunch of problems. And here you have the midterms for review. These are midterm problems. Yeah, I would just say that Milagros. Yeah, we're going to look at that. We can look at that next week. Okay, so you guys, great. Okay, so let me do, okay, so wait, Elizabeth has a question. All right, so I'm going to do the overview of normal distribution, and then we can look at specific problems. Just to wrap up, is this okay then, what I said about the skewness? So don't worry about your number being different from this. If you use Excel, it should arrive at the same conclusion, but maybe they use a different formula. Okay, but this is probably the unbiased estimator for skewness, because it looks a lot like the standard deviation calculation, but it's not. It's not the standard deviation calculation. Okay. So where am I going? All right, so I begin with a discussion about, okay, hold on 1 second. I'm gonna get some water. Let's take 5-minute break, okay? I'm gonna get some water and settle in. Let's take 5 minutes break. I'll see you back here at 10:55. I'm gonna pause the recording. So we're fresh. We had a snack or a drink. And we're ready to review or introduce the normal distribution. I'm going to share my iPad with you. So this is what we were just talking about. All right, so I begin with a discussion of the histogram. So you had you should have watched the video on histograms. I explained how to make a histogram. And from now for this unit, okay, so this module, we're gonna focus on symmetric histograms. Sorry, I'm echoing. All right. Okay, so we're gonna focus on symmetric histograms. So here is here's a symmetric histogram. Most of the observations are in the middle. Some of them are on the right, but just as many are on the left. Another way to say that is some of them are higher than the general, the most likely observation is in the middle, and then a few of them are higher, and then just as many are lower. But then there's out here, there's very few, but there are some that are much higher, but also there's some in the same quantity that are much lower. So this creates a mirror effect through the center. What you have on the right is almost on the left. Now, in reality, histograms that are symmetric aren't perfectly symmetric like this, right? But we still call them symmetric. And the way you can look for symmetry is to check if X bar, the mean, and the median are in the same class, so your same interval. If the mean and median are the same interval, you're going to find that you have a symmetric distribution. Remember, because we talked about skewed, that the median would be pulled away. The mean would be pulled away from the median if it was right skewed, and the mean would be pulled away from the median in the left direction or lower if it was left skewed. So if they're in the same class, we usually say that the distribution is symmetric. All right, so density curves. So now density curves. What are density curves? The density curve is, we talked about this last class, about smoothing out. When I smooth over, and create a curve like this, what I'm saying is that if I had more data or all the data, I believe that any anomalies, any kind of awkward looking, any gaps here would be filled in. It would fill in all the space and this would smooth out. And that would happen if I had more and more observations. You would have finer and finer rectangles or bars, and that gap would fill in. So that's what you visualize, okay? And that's what you're supposed to think about. So if but let's say we had more data and we can be more precise, then my bars could be thinner. Because I have more data, looks terrible, but I hope you get the idea that the bars, I make them a little bit. Okay, so notice you're gonna have less gap than if I smooth out between these two. There's this gap here. That gap would fill in if I had finer interval or classes. So that's what the smoothing idea is. All right, so one person might smooth different from another depending on their interpretation of the phenomena, their interpretation of what they see in the data and what they know about the characteristic they're studying. We believe it's just gonna, end up like that anyway. So we're gonna focus on symmetric distributions. I'm gonna talk about this being the variable here on this axis. So for histogram, the variables on the horizontal axis, and the number of observations or the percent of observations are on this axis, the vertical axis. When we're talking about the percentage of observations, we are referring to what's known as the relative frequency histogram. And I make a video, I explained that we use the relative frequency histograms in statistic as opposed to the frequency more often because of a reason. What was the reason I explained? Why do we use the relative frequency histogram instead of the frequency histogram? And just to be clear, that's when it's percent of observations. That's relative frequency. You remember? No. We do that because we, in the middle here, these are the percentage of observations. And as a result, for every relative frequency histogram, we interpret that under the curve, under the density curve, are 100% of the observations. All the observations. This differs from a frequency histogram that has, 60 observations or 20 observations or 15 observations. It makes it possible when we interpret, we can talk about very easily. I can mark here and say, okay, what's the chance? Oh, sorry, I can mark here and say, okay, let's say I'm interested in knowing how many observations are below this. How many observations are below this value? Now, from the graph, we know it's 50%, right? So what we do is I mark this with an X. I say this is the value X of this variable. So I use the example. I use throughout this module, I use the example of height of women, for example. So example X, which represents the random variable height of women. But the little x represents the value along here. So let's say I let x be 64 in the middle. And I use the relative frequency histogram. And I could say, what percentage of observations are less than 64? And from the graph, you know what it is, right? What percentage of observations are less than 64?
50%.
So this is in inches. Let me stress, or let me put it here. So this is 50%. So this is how I express that for the variable x. In other words, you can say this as, you can read this as the height of women less than 64 inches is equal to 50%. Okay, so P stands for percentage. Or proportion. Or frequency. Or you could even say relative frequency, which is what it is. As a percentage, that's what P stands for. Okay, percentage, proportion, frequency, relative frequency. And also, because I'm going to say that I believe that this histogram represents the population of women, and I'm going to introduce the symbol mu as though this is representative of the population mean. So I'm going to make a leap. Even though it's just the sample mean, so I put it in the middle, it's just X, but it also happens to be the sample mean. What I'm saying is that also, I think that the probability or the chance that a woman is less than 64 inches tall, the probability is another interpretation because of the fact that I'm using this to represent my population. So I can talk about out of all of the possible outcomes, 50% of them are less than 64. That's like talking about the probability or the chance. Okay. The chance that the height of a woman will be less than 64. All right. So note that I emphasize the number line here, that it goes from all the negative values all the way to the positive values. So that's basically how we're going to use this. So I'm just going to introduce some notation that am I going too slow? Because I do talk about this in the video. I just want to review a bit more the notation that I'm using. You can tell me if I'm going too slow. I can speed it up. So let's say that these bars add up to a total of 10% of the observations. And I'm going to say this is X. And I'm going to put just a star on it. I'm not going to give it a value. How would you write that? How would you express that? How would I write this as a statistical sentence? So I say the chance that X, big X, is less than little x is equal to 10%. Okay, so that's the way to refer to. I can give a number to it. I can put a number there. I'll do a number on the next one, but I just want to show you the general form of it. Okay, so let's put a number on it. Let's call it let's say it's 50. Let's say it's 50. So what is in between 50 and 64? What's the chance of being between 50 and 64? So we can write the probability, and now you're going to put the big X in the middle, and this, so you're going to go in, again, numerical order, put the smaller number here, 50, sorry, not 50, yeah, 50, and 64. This is in between. The chance of a woman's height being in between 50 and 64 is 40%. So that's how we interpret with the relative frequency histogram. So we talk about area to the left, known as, what's the word for that, area to the left? Area to the left corresponds to calling this value a percentile. So we call, what is X star? What's the percentile value of X star? Let's do this one. What about 64? 64, which percentile is 64?
The 50th percentile.
Yes. What about X star or 50?
That would be the 10th percentile.
So percentile is defined as the observation where P% of the observations are to the left. It's the observation with P% of the observations to the left of it. So 64 is the 50th percentile, 50 is the 10th percentile. Okay, I'm going to give you one more. I'm going to put in a different color because this is getting messy. What do we call 73?
That would be then 95th percentile.
Does everybody get it? Yes, you're right, Sal. So we write P. We can write it two ways. X less than 73 equals 95%. Because on the left is 95%, but that's not what I drew here, right? So it's the 95th percentile, but the way I've drawn it, I can also emphasize that I'm going to erase this out of my screen. All right. So less than 73 is 95%, but greater than 73 is 5%. So we can call this the 73 as the 95 percentile, but it's also marks the top 5th percentile. To make it go to the right, you have to reverse the direction, or the upper 5th percentile. You have to tell the reader to look this way. Otherwise, just saying percentile is always to the left. Percentile is to the left, these arrows. Okay. Questions? Chat. So it's the 95th percentile, but it's the top 5th percentile. So the arrow is really important, okay? The arrow to the left makes it a percentile. The arrow to the right makes it a top percentile, top 5th percentile. Okay, any questions so far? I have a question for you. Can I make this an equal sign here? Can I also make it equal? Does it change anything? Does it change anything if I put an equal there? Just take a stab at it. What do you think? Does it change if I put an equal there? Yes or no?
You mean instead of the arrows?
Arrow with an equal, greater or equal. Can I do that? Put it there. What do you think? Can I put an equals there? What happens if I put an equal there? Does that change anything? Christian put his neck out and said, no. What do you guys think? Misael says it stays the same. What do you guys think? The rest of you. Right. Okay, it stays the same. It does stay the same. It does stay the same because, so some books will write the equals. I'm just going to leave it like this for now, but it doesn't matter because why? Because what I'm saying is x equals 73 is equal to 0. There is no density, there is no area at a single value. Always we refer to the area to the left, the area to the right, or the area in between. We do not have area under the density curve. We do not have density, area, space, observations. We don't have them at a value. Okay, it's just 0. So this is a characteristic of continuous distributions. So this distribution is continuous. You see, I have a number line here. It's different from a discrete distribution where you can't have decimal values. Technically, you could have decimals. I could get a very precise reading on a person's height, 64.3 inches, right? But okay, so some of you are just figuring that out. Okay, so if ever you're asked, you got to remember this because at least you'll get one of the multiple choice questions right. If I ever ask you for a continuous distribution, what is the probability, percentage, proportion, frequency, relative frequency of x equals a number? It's always 0, okay? But that's only true for continuous distributions. So the answer is it stays the same. It doesn't matter. It doesn't change anything. So some textbooks just put it in. Because that way, when they work with continuous or discrete, they'll always, distinguish between the equals, but. All right, so most of you guys didn't know that, but that's right here in the notes. It says, to review, the area under the density curve is 1 or 100%. The area under the density curve of any one particular value is 0. Area only exists between a range of values. Just think that there's no density at a single point. Consider the number line here. Let's say, see. I guess the way that I explain this, I don't know if this is helpful, but what's the next value after 73 on this number line? What would be the next number? So 73 is here. What's the next value right beside it? What's right? Okay, 73.05. Oh, yeah, so you guys wrote some things. Okay, so yeah, like basically the next value, there are infinitely many values between 73 and 73.0000000000001. Between here and here, there's infinitely many values. Okay, it's like, because it's continuous, theoretically, I could go forever. And when I touch one value, I mean, how thin does my line have to be that I just touched 73? So it's like saying, to be at any one single value, since there's infinitely many, even just between 73 and the next value, to be at one value, the chance of being just at one value when there's infinitely many is 0. That's how, I don't know, I have that interpretation in my mind. But really, there's no density. We do not interpret this graph at one value. It's just, there's nothing. You have to take a range of values. So even if you did 73 to 73.05, you'd have area there, but not at 73. Anyway, that's one way I put in my mind to remember that. Okay, so that's just for continuous distributions. All right, the third point that we discussed is the pth percentile is the value such that p% of the area under the density curve lies to the left of it. Okay, so those are the 3 points about density curves. I just use this to do more problems, but okay, so I did it above. And number 4, because density curves are idealized, in other words, we imagine that we have all information possible on the variable when we are smoothing out the underlying relative frequency histogram. When density curves are symmetric, we give a special name to the center as the mean, mu in Greek letters, stands for m, and a special name for the spread or standard deviation, sigma, which is the Greek letter for s, lowercase sigma. Okay, so those are the 4 points in general of density curves. But now you have a special type, not just density curves, sorry. Let me say this. So imagine the universe of density curves. And then there's a subset of them that are symmetric density curves. And then inside of the type of symmetric density curves, there are normal density curves. Are you guys following me? So just imagine all the possible density curves. A subset of those are symmetric, and a subset of the symmetric ones are normal. So what is normal? What is normal? Normal is a special property, and I introduced it last week. If you have a normal, sorry, if you see a density curve that is symmetric, it has one peak, because a symmetric one doesn't have to have one peak, right? This could also be, you could say that's symmetric, but it has two peaks. It's not perfectly symmetric, my drawing, but this has two peaks. That's not normal, okay? It has to have one peak and a bell shape, which we'll describe more details. There are often density curves that have these properties, but normal distributions is special. And it's special in that it observes the 68, 95, 99.7% rule. So we begin by, we can draw it. I'm going to show you. If you calculate, you take the data and you calculate the mean, you can rename it the mu. You can calculate the S and rename it sigma. And you can get this drawing that I'm going to put here. And if you watch the video, I explain that you start, okay, I'm going to start in the middle. I guess this is the middle. You're going to name it mu. And you're going to put a dot up here. And you're going to draw a curve. And then you're going to draw I want to flip it. It's okay. Okay, and you're going to continue to draw it the other way. Say it's like that. And then where the curve goes down but then starts to go up, we're going to mark here. So where the inflection point is, where it turns from concave to convex, concave to convex. You guys have contacts, you know what that means. You need to put your contact on this way. If it flips like this, you don't put that on, you flip it over. But okay, this is 1 standard deviation. This distance is 1 standard deviation distance. And that marks there too. So going 1 standard deviation in each direction, this area is most of the data. Most of the data is 68% of the observations in between. Then using the same interval on both sides brings you to 2 standard deviations. So we write that as 2 sigma, and on this side minus 2 sigma. That's 2 standard deviation, and that covers I'm gonna erase this. "95% of the observations." And the data doesn't end there. You also have data outside up to 3 standard deviation and even beyond. Within 3 standard deviation, you have practically all the data, but not all of it. You have a remainder here because it's 99.7, that leaves how much on each tail, each side? Since it's 100, how much does it leave on each side?
2.5 and 2.5.
It's
Not 95,
oh.
this one here.
Oh,
0.50%, 0.15 or
15, yeah. So it's going to be, okay, so basically you guys, you realize it's 0.3%, so it's half. So 0.15%, I can also write that as 0.0015. So normal distribution is spread out in such a way that 68% of the observations are within 1 standard deviation, 95% within 2, and there's still some outside of 3 standard deviations from 99.7%, still 0.0015%, oh, sorry, 0.0015 of the observations are going to be outliers on either side. So 0.3%. So for instance, I think I said this last class, if n is equal to 10,000, how many outliers are there? If it's normal. So let's say if n equals 10,000, assume normal distribution. And you don't just assume it outright. You check, right? You check. You check to make sure this is true. So you draw it, you make a histogram, and you can count. You can find the mean, the standard deviation, and check, like I did last class, how many observations are within 2 standard deviations, how many are within 3, and what if you assume or you find you have a normal distribution, how many outliers should there be?
would there be at least 30 outliers?
So you're going to take 10,000 times 0.003 is what?
30.
Exactly. That's how you do it, okay? So that's what the percentage is used for, right? So this is your n. Of that, so this is of the 10,000, you expect 30 outliers, 15 on one side and 15 on the other. And remember the rule for symmetric distributions, outliers are outside of 3 standard deviations. So we'll call those statistical outliers. How you doing? So that's my introduction and review. Of this introduction, because I still have more to do. So, questions? So I said here, if you can't read my writing, Assume you have a normal distribution based on, and you base that on your calculations of the mean and the sigma. You would expect to see 30 outliers out of 10,000, if n equals 10,000. Okay, then I give you some examples here. So remembering that X bar and S are statistics, right? Because a statistic is a number computed from a sample, and they're used to estimate the parameters mu and sigma. From what I've described to you, all that really matters here is mu and sigma, right? If I have mu and sigma, I can draw this. And once I draw this, I can estimate. That's really my goal. I want to be able to estimate certain outcomes. I want to estimate I want to estimate what are the possible outcomes. So this is like our model that we're going to use. So what we say is that this distribution, so we're also going to refer to this variable, whatever variable we have, I usually use the symbol X, and we write this tilde sign. This means distributed. As, and you put an N for normal. You put the mean, and you put the standard deviation. This is how we express this. Once I say N, the reader should know that it has this layout, 68% in 1 standard deviation, 95% in 2, and 99.7 in 3. Okay. Did you need to copy that? So we do that because once we know it's N, then all we need is the mean and the standard deviation to be able to make estimates. I make a point here that you could have this could be normal. This could be normal. This could be also normal. Trying to do this to scale. Oh gosh. Okay. But this is showing you, because I need to have 68% within 1 standard deviation. Call this A and call this B. So a flatter distribution has a larger standard deviation. A more peaked one has a smaller standard deviation. Okay. And that's because this area, if it's more narrow, this area has to fit in there. like Jello, a different Jello mold. I have the same amount of Jello, but it still has to fit in there. So that makes it more narrow. Okay, then I just repeat myself here. This is known as the 68, 95, 99.7% rule. And I make a point here that this is the function for the normal distribution. This is the function. Now, I don't expect you to memorize that, but I do want you to look at it and tell me what do you see there that you recognize? So this is the function, like as if we're going to draw it. What do you see there that you recognize? That's relevant to our discussion just now. What do you see in the formula? Nothing? Comments? I don't see your comments. No, Carla, do you see the normal distribution? The mu and the sigma. That's what I want you to say. You see the mu and the sigma right there, you see? And now like pi is a fixed number. E is a fixed number. All that's going to matter is look at this other sigma over here. Sigma, sigma, mu, and x. So mu, sigma, and sigma will be calculated, like you'll be able to calculate those. And then the x can vary. And this shape is going to end up looking like this. The point is, what matters for the function from to make it different, to make different normal distributions is changing the mu and sigma. So Adaira, thank you for writing that. Okay. So you don't need to ever see this again, but that's the function for the normal. And it's a continuous function. And in a higher level course of statistics, to find the area, you would integrate this function to get the percentile area to the left. That's why you learned integration in calculus if you took it to do things like this. Okay. Well, we're not going to do that in this class. All right. So here's another example that I give, but using particularly this example of 100,000 height measurements of women where the mean is 64 inches and the standard deviation is 2 inches. And we see the shape is symmetric, single peak, bell-shaped, and we feel we can assume the height of women is normally distributed, and we can draw the curve here. And then use that to make estimates. So I have a bunch of examples here where I make those estimates using the curve. And I'll just refer you to look at that. But what's more important is that it falls apart. Like we can't rely on that graph exclusively. We need more details to answer more detailed questions. So let's just do a couple of problems so I can show you what I mean. So rather than drawing this again, I'm going to steal this one. Let's take this one over. That didn't work. All right, let's see if we can answer a couple of these. Well, first, actually, well, let me make it comfortable here. All right, so I'm gonna put the values in now, right? So we got 64. And 2 inches was the standard deviation, so I can. I can make this 66, 68, 70, right? And 62, it's easy, 60 and 58. Everyone saw that? So that's my distribution for this problem. So using this as a model, what is the chance? Okay, this is how we write it, okay, just to be clear. So remember the between, the chance of being between 62 and 66 inches tall. So if you took one woman, what's the chance? So the next woman that walks into the mall, what's the chance of her being between 62 and 66 inches tall? If women's height in Puerto Rico is normally distributed, then the chance is 68%, because 68 percent of women are between that height. This one, there's a 95% chance of height being between 2 standard deviation. That translates into 60 to 68. So 2 standard deviation, 60 to 68, 95%. That's what that says. And between 58 and 70 is 99.7%, you see? So what about 66? How are we going to figure out one that's not explicitly on the chart? So we want to know, what's the chance of being here? So I'm going to redraw this here. Just to show the 66. So it's going to be like this, because it's kind of getting crowded over here. I'm going to show the 66, which is like here. And I want to know, this says the area to the right of 66. So I put the arrow there. And what are you going to tell me from the graph below? What will that be? Well, it's 68 up until here. Okay, we'll do number 3 as well, Aritza. Okay, so we have 68 in between here. So this one, so this is the, okay, there's different ways you can do this, but I'm going to show this way. So 68 in between, but 100% minus 68% equals 32% outside. So inside of 1 standard deviation is 68, outside is 32, but there's 2 outsides, there's 2 sides. So it has to be 16% on each side. Is everybody okay with that one? It looks like. Right, okay, so you guys are good with that. So that's 16%. So the answer here is 0.1600 or 16%. I'm putting 4 decimals and you'll see why later. Good. Okay, let's jump. Well, anyway, this one's easy. Let's do this one. The left side. So the probability proportion percentage that a height of a woman walking in the room in Puerto Rico is less than 58 inches it's right here. So we'll use it. So that's going to be the answer, right? So how do we get that answer? It's 99.7% in between 58 and 70. We just want the left side. And it happens to be right here beside the question, 0.15% chance. It's very small. Okay, let's do number 3. Let's draw it again. I don't have to draw it for the second one, but for the third one, I'll draw it again. So you can get used to drawing. It's hard for me on glass. I guess some of you are using a tablet too. Right? So 60, where's 60? 60 is over here. So I'm gonna draw it like copying over here, but I want to go right. So I want to go right. So this, oh, sorry, I didn't put the number 66 there. I'm gonna put it here. All right, so what is the answer there? Hey, there's different ways to do this. Okay, so you guys got the hang of it. So the in between, so you look where 60 is marked with its pair, okay? Its pair is here, 68. Between 60 and 68 is 95. So it's 95% up until 68, which I don't want to mark, but I'm going to put it just like that. But then you also want to continue. You don't want to stop. You don't want to make it 95. You want to continue. So what is this area here? 100% minus 95% divided by 2 is 2.5%. So that's how you know what's there. So you have the 95 between and the 2.5. So the answer is, you guys did well on this, 97.5%. Got it. You guys got it. Okay, so this is not hard. This is easy. What's hard is if I ask you about values between the tick marks, larger 1, 2, and 3 standard deviations of the mean. You're going to be guessing or approximating, and we want to learn a more systematic way to do this. So I have all these problems. Oh, by the way, what's the answer to this one? X equals 82. What's the probability? Aha, very good. So you guys know now. It's like easy points on the test, okay? Always 0 when it's equals. So I have the exercise on video here doing all of these if you want to review that. And then I get to the point that I can't do these very well. These ones are off. You know, I have 58. I don't have 55. I have 60 and 68. I don't have 65. And then what's this? And so it becomes confused. And 40, what in the world? 40 is way off because I end at 58 and 3 standard deviations. So these ones are a little bit off, but you can review those, how I manage those and how I discuss those. But this brings me to a special standard normal density. Now, remember back what I said about the density curve universe over here. Where did I say it? I think over here. So I drew this for you. So I said, out of all possible density curves, some are symmetric, and out of the symmetric ones, some are normal. And out of the normal ones, one is called standard normal. And because it's so special, it gets a special name. We refer to it as a Z distribution. So these are distributions that were derived by statisticians for their use in making estimations. But very explicitly, they have a pattern, you know, and they tested that pattern in nature, and they found that for large standardized, not in nature, but in society and nature, and the normal distribution is good at describing the results of large standardized tests like the SAT or the College Board, also for like LSAT and MCAT, those kinds of large standardized tests. It's also seen in height and weight distributions, and it's used in science, medicine for estimating, okay? So you're with me, right? So there's just the one standard normal. The Z distribution is special, and we're going to use it to help us solve problems. And what is special about it? The standard normal distribution has a mean of 0 and a standard deviation of 1. And if you draw it yourself, you'll see why it's so special. We're going to use a large Z to represent the curve or any value of the curve, and little z to represent a specific value. And we're going to continue to use our notation that I introduced with the x's, but Z is a standard normal density. So if I was to draw this, it looks like a regular normal density curve. Oh, I better make a line. And the mean is 0. One standard deviation from the mean is what? And 2 standard deviations is what? And 3 standard deviations is what? So I'm supposed to use mu and mu plus sigma. So this is just 1. And then this is mu minus sigma, so it's -1. And this is mu plus 2 sigma, which is 2. And this is mu minus 2 sigma, which is -2. And then this is mu plus 3 sigma, which is 3. And this is -3. So what do I see here? Whereas in this drawing, 66 was 1 standard deviation above the mean and 62 was 1 standard deviation below the mean. Now my numbers are corresponding to the distance from the mean. So this is a relative measure to the mean. This is 1 standard deviation from the mean. Its name, its label corresponds to its difference from the mean, okay? Relative measure. 2 standard deviations from the mean is just 2. And 3 standard deviations above the mean are 3. If I'm below, I use the negative. This is 1 standard deviation below. This is 2 standard deviations below. And this is 3 standard deviations below. Any questions so far? This is just a review for people who already did their review. I'm just trying to bring people who didn't on board. Okay, so why is this so special? Well, for one, any number that I tell you, if it's standard normal, you know where you are relative to the mean. You can visualize it. And in fact, statisticians provide a detailed set of values to help you make estimates, not just 68, 95, 99.7. They provide a lot of value in these tables that are on page 22 over here. These tables can be used for more detail about what to expect. Okay, so I'm going to ask you guys to review the table explanation. I'm going to do this quickly with asking you, what is the lowest value on this table? So here's the curve here to give you an idea. What is the smallest value on this curve? So this is the z-score. We call it the z-score.
Negative 3.49.
Negative 3.49. And then this is the value here, 9, and it corresponds to inside the table here are percentiles. This is the area to the left of this value. So this is going to be this one, 0.0002. Okay. So we're beyond 3 standard deviations. It's going into the outlier area. So that's helpful. But anything off this table, if I asked you to find the percentile, the percentage of observations to the left of -4, what would you say? What would it be? Arisa, right, 0. Okay, so there's nothing there. So that's how you read the table. And the table, as you go down the table, you're moving along the curve this way, all the way up till 0. It'll take you all the way to 0. So it's going to go from there to 0 here. And then we also have the positive table, which is here. Now that will continue from the 0 forward. And what is the largest value on this table? And very good. So that's going to be over here, 3.49. Remembering that the table gives you the area to the left. So what it tells you is that the area to the left is very big. It's almost 100%, 0.9998. So if you had, sorry, I put a Z. I meant to put a Z here. I put an X here. Don't confuse you. This is Z. Z less than -4. If I did the same thing here, Z less than 4, what would be the answer? Careful. Left is 1. I went left. If it was Z greater than 4, what would it be? Z greater than 4. If 4 is over here. There's nothing there, right? 0, 0. Z greater than 4. Z less than 4 is 1. Z greater than 4 is 0. Okay. Let me go back here and do the extreme on this one. What if Z was Z less than -4 is 0? What about Z greater than -4? Great. Okay, so that either you're going this way, 4 is over here, and you're going this way. It's the whole curve. All right, so those are the extremes of the table. And how do we use this table? So I have a lot of exercises for you to practice. I want to go to the ones I don't have answers for. So I have all these answers here. So I want to start over at the end. Oops, I went too far. Why did I go so far? Is that possible? Oh yeah, because I'm at the tables already. Okay, here. So here is an example. We have time to do this. So Michael Jordan's height is 78 inches. Men in general have a mean of 69 and a standard deviation of 2.8. Women in general have a mean of 63.6 and a standard deviation of 2.5. Which Rebecca Lobo's height is 76. Which player is taller? How will we answer that question without looking at the answer? So what I explained to you is the relationship between any variable that's normally distributed and Z that is normal with a mean of 0 and a standard deviation of 1. To move from a regular normal distribution to the standard normal distribution, you need to recenter and standardize the values. And you can do that. The relationship between X and Z is found as you take the value, any value, and you subtract the mean, so you center it at 0, and you divide by the standard deviation to convert it to the number of standard deviations from the mean. That's what the Z is. So what we're going to do is convert Michael Jordan, his height, into standard deviations from the mean of men. So it's 78 minus 69 over 2.8. And we're going to do the same for Rebecca Lobo. Now, when you make that calculation, what do you get? You get 3.21. And 4.96. So she is relatively taller. She's taller because she is way in the outliers for women. He's an outlier for sure, but she's way in the outliers. Okay, so she's a taller person. So this is how we make numbers comparable, normal distributions comparable, or numbers of relative distributions comparable. We standardize. Any questions about that? Now I can convert this using the tables that I showed you. You can find the percentile, what percentage of people are shorter, or men are shorter than Michael Jordan, what percentage of women are shorter than Rebecca Lobo. It's probably 100%, right? Because we said at 4, it's already 100% on the left. And there's still some people that are taller than Michael Jordan, or some men that are taller than Michael Jordan. All right, so that's one thing I want to show you. I have 15 minutes left. Any questions about what I did here? Can you see it? It's a little light. Okay. And let's do a similar problem. So Eleanor and Gerald took two different tests for entry into college. Now these have to be standardized so they can compare the students. So who has a better score on their standardized test? So for Eleanor, you need to calculate standardizing 680. And for Gerald, you have to do the same thing, but using his group scores. Okay, so you should get that Eleanor is 1.8 and Gerald is 1.5, so she is the better student. What percentage of students are score less than Eleanor, and what percentage of students score less than Gerald? That's so now we're going to go to the tables and look for the area to the left. I have many exercises you're going to practice going to the right, going between. So you're going to practice that in the meantime. Eleanor is 1.8, Jordan. And she's the best of the two. Good. So let's go to the tables. 1.8 on the table, the positive table is right here, 1.8. Now this is for the second decimal. It's just 1.80. So 96.41% of students scored worse than her. 96.41. And for Gerald, 1.5. Let's look at the table. For Gerald, 1.5, 93.32% of students scored worse than him. Right. Good. All right, so that's all straightforward and easy. Now we're going to ask, we have 10 minutes for me to work on the backward type problems. The problems I call type 2 problems. Z type 2 problems in my description. What score will Gerald have to get to be in the 99th percentile? He's only in the 93rd. So I'm going to write that like this, but what I'm going to do is draw it. I'm going to sketch it so I can understand or convey to you what's going on. So here is the Z. When I draw, I'm always drawing the Z distribution. Don't draw the X's. You're going to get confused. Just draw the Z distribution. So I'm going to draw, even though there's X's here, it's referring to X because it's going back to the score and not the standard normal. I'm going to draw the Z variation because it turns out that the position on the Z is in the same place relative to the mean as the position on the X. So I'm going to use that fact. And I'm going to mark where 99% is. So remembering that the percentage is under the curve and inside the table, but on the curve is the value. So Z is what I want to find. And I want it so that there's 9999. Oh, no, too many nines. 9900. And that's why I have 4 decimals. So now you see why I'm keeping 4 decimals. My first step is to, in this type of backward problem, is to find, so I'm doing things backwards, okay? If I give you the values and I ask for the percentage, you do what we've been doing, standardized. and using the table for the Z score, to find the percentages. So if I give you the value of the score or the weight or something, you can standardize and then get the percentage. But the backward problems are in the reverse. I give you the percentage and I want you to find me where you are, what's the score, what's the Z score, and then what's the actual score on the test. What's the actual value of the variable? So to do this, I have to perform the operations backward as well with the table. I need to look for this value on the table. It'll correspond to the area to the left and find the corresponding Z-score. So I look at the table for 0.9900. And I have to obviously use this table. And the way this table runs, you got to be careful, is like this. Oops. You got to read it this way. It's backwards. It's like reading Hebrew or Arabic. We're reading this way. So 0.99 here. So between these two, and you do have to watch my videos, okay? I'm giving you a really quick overview because there are some cases that you need to be aware of. Which one is closer between these two to 0.9900? I think it's this one, right? 0.9900 is this one, 2.33. Now, if these were the exact same number, which does happen down here, look, these are all the same number. When it's the same number, you need to average between the two. And which two is that? You're going to have to go between like the middle value of the same ones. And if there's just two of them, you have to average them. So for instance, where's this two? Anyway, so it depends on the question, but you need to average. But if there's just, in our case, where were we? We were here. This one is closer. You go to the closer one, or if they're the same, you average the ones, right? So it's going to be this one, and it's 2.3. 2.3 and 3. 2.3 and 3. And now what? So I have 2.33. So what does that mean? This is 2.33 standard deviations above the mean. But I need to translate that in my step 2. I need to translate that into Gerald's score. So what's the mean? What's the standard deviation? It's up here. For Gerald's group, I need to use these values here. So using these values, I'm going to put it back in blue. 2.33 standard deviations above the mean. You see how I did that? Just saying it out loud. This is 2.33 standard deviations above the mean. And this is 2.33 standard deviations, so that's multiplied above the mean. Can you hear me? I'm going to put my microphone close. Oops.
Yes.
So that is it. And this is actually my X, the big X I want to find, and put it all together and you get the answer. $31.98. Very good. So I feel like I think you got it or understood it. Now you hold on to that thought. Let's do one more. Sorry, 31.98. Okay, so 31.98 was her score. What would have to be his score? Oh, it's really high. on the ACT. Is that right? This seems really high. 2.33 times 6 equals plus 18. Wow. Okay. So anyway, 31.98 to be in the 99th percentile. And he earned, what's his score? .27. Okay. That's not bad. All right. One more problem. This is the one below. What score would Eleanor have to be in the top 5%? So don't freak out. It and go from there step by step. We're going to draw it. And we're going to be here, top 5%. So this is 0.0500 in the top 5, which is also the same as the 95th percentile. So you can write that. Either way, what I want is the Z. It's a backward problem. I give you the percentage, 95 you can think of, or the 5%, either way. And you have to give me the score that Eleanor would have to have. So first, step 1 is to use the Z to do this. Remember, we draw the Z's, not the X's. That's going to really confuse you. So we're going to look for 95 on the in the table because the table only gives the area to the left. Don't forget that. So we got to go to the table and look for 95. And let's see. 95 inside the table is, remember, it's 95. Oh, it's over here somewhere. 95. Okay, 95. Aha. I have two values that are very much, well, they are the same distance from 95. This is 0.0005 below, and this is 0.0005 above. So I have to go between, and between gives me an average of these two is 1.64, and halfway between will be 4.5. Okay, 1.645. Milagros wrote it, so that's good. So 1.645, if you guys didn't catch it, watch this video again at the end. So this Z is 1.645. And then step 2. This means 1 standard deviation above. Now you might be below sometimes, and you got to be careful to do the below the mean part. 1 standard deviation above the mean or from the mean, because if it was negative, you would multiply by a negative. It doesn't really matter because you're just going to add a negative. So this is x equals 1.645 standard deviations. Now we have to go up and get Eleanor's information. Careful. Get Eleanor's information and take it down. Whoops. Take it down. Oh, I screwed up everything. Do this again. Oh. What happened? Okay, do it again. All right, Eleanor. So it's 1.645. Standard deviations are 100. Plus 500. And that's what she needs to get to be in the 95th percentile. But she's already above it. But anyway, it's just for us to practice. So we multiply 1.645 times 100 plus 500 is 664.5. And that's that. So I've done a little bit of everything for you. And I encourage you to finish this weekend so you can start the regression materials. Next week, I'll answer any questions you have about normal distribution, and then we'll do the regression review. And we can start studying, we can start maybe doing problems overall, right? Just for the test. And then I'll leave you that week to work on the midterms. We can even do midterm problems next week because regression doesn't take too long. All right. In the regression unit, you have to, there's only like 13 or 12 pages that are required to read. The other ones are extra for students who are more advanced or they want to link it to other things that they know, they can read that. I mean, you can all read them. It's just for a time, in regard to our limited time, I'm just encouraging you, but yet you just have to read the first pages that I mentioned. All right. Okay, so what I'm going to let you guys can go if you have to go, and I'm going to finish the connect. I'm going to look at the connect problems for everybody, and you guys can check back with the video. Okay, you can check back with the video about the connect problems. All right, or you can stay. You can stay. You can watch me struggle through that. See what's going on. Okay, so have a good week.
Thank you.
Thank you. You too.
Bye.
Thank you.
Thank you, you too.
Thank you.
Thank you.
Thank you.
Ciao. All right, let's see the connect. I got to open connect. Yeah. So different is the answer. So to explain this again, so this problem, someone said they did put different, but it came out wrong. So send me a screenshot of that, who had that happen, okay? I'll check the chat too. But yeah, it's different. The advantage of the randomized block design over the completely randomized design is that we are comparing the treatments by using different, like women and men. They're different in the characteristic. But they're getting all the treatments, but they're different types of experimental units. I don't like the sentence, but that's the answer there. It should come out correct. Anyone who got different as wrong should let me know. And then I can just cancel this question completely. Any questions about that? What was the other one? Showing you all the answers right now. Okay, I think it was in the other one. Oh, you're not seeing it. Okay, you're not seeing what I'm doing. Oh, that's good. Okay, good. I thought you were watching. Okay, good. I'll go back and show you what I was staring at. All right, I'll share this with you. Okay. Says the advantage of the randomized block design over the completely randomized design is that we are comparing the treatments by using different experimental units. That's the correct answer. Because you have women and you have men, they're different. They're getting all the treatments, and we're checking the treatments on different classifications where to save money, and have less in time, which is money still, we're going to separate the groups by group of people who will react differently to the treatments that we're already aware of. So that's different. So that should be the answer. And if it's not, the person who didn't get different as correct, let me know, take a screenshot, and I'll just erase this question. So I think it's poorly worded. Okay, let me stop sharing for a second.
Professor, that my homework is already blocked. Is there any way that I could see
Oh, your homework is blocked because you
Yes.
had 100%. I think that's why it's blocked.
Wow.
Yeah, when you get 100%, it blocks it. And let me see if I can fix that. Hold on. Some other students are frustrated. I have to go through the settings and edit the assignment. But once it's open, I can't edit too many things. I can't edit everything. Let's see if I can change. I'll show you what I have here. Share. So you see how it is, edit all settings, scramble the questions, revise the previous attempt, allow for study attempts, unlimited attempts, resources, you get to see the points in the book, and I have it set up so show feedback after submitting each attempt. Select the students will see total score before the due date and all detailed feedback after the due date. But then if you get 100% detailed feedback, so I have to say, see, the problem is detailed feedback with solutions. It's not going to show you that because I said hold feedback. So that's why it's blocking it. It's after the due date, it will show you. But yeah, you want to see it, right? So total scores before the due date, all detailed feedback. It should be the same, but some reason this doesn't work. Okay, I'm going to turn this on and you can tell me if you can see it now. Okay, try and see if you can see your quiz. Oh wait, I have to assign it again. So check assignment 1 that you see your 100%. Are you checking? Yeah, I'm just gonna look for the other one. Gauges. Ages feature a single measure showing variation over time. I have to go into the book.
Professor, for assignments, the score that will be recorded is the greatest score, or
That's right.
because okay, because I see that the connected average the attempts.
Right. Yeah. I don't know why it does that by default, but yeah, I'll pick the highest.
Okay, thank you.
Yeah. So did you check if it shows everything? You see your score? Okay, you can see it,
Yes,
Carla? Good.
I show. Yes, I
Okay.
can see now the score.
Okay, good. So I'm gonna look for this gauges, but what happened to the search bar? Gauges must be a term. See, that's the thing about the book. There's some things that it talks about that I don't talk about. So I have to check. Oh, it's not gonna be easy. So this is in chapter 2. Oh, here. Dashboards and gauges. Okay, let's see. It's optional. I probably should drop the question if it's confusing. Let me share with you. Dashboard and gauges. In the lower left-hand portion of the dashboard, we see 3 gauges depicting the percentage utilizations of the regional, short haul, and international fleet of the airline. In general, a gauge allows us to visualize data in a way that is similar to a real-life speedometer needle on an automobile. The outer scale of the gauge is often color-coded to provide additional information. For example, note that the colors on the outer scale of the gauge range from red to dark green to light green. These colors signify percentage fleet utilizations. Okay, so what was the question? Well, if I understand this properly, it doesn't show a single, well, it shows a single measure, does. These colors signify fleet poor and satisfactory to good at least. While gauge charts are nice looking, they take up considerable space. Guess it doesn't show a single measure. This is a bad question too. It's not clear. Gauges feature a single measure showing variation over time. False. I think it's just it's supposed to not be clear. Gauges don't show variation over time. That's why it's false. Gauges don't show variation over time. Okay, so that's my answer to that question. Gauges are just that, like a speedometer. It's not about time. I think that's why it's false. All right, so that's what else? What other question was there? Let me check the photo again. There's one in the photo, I remember.
I think it was mine, and it was about the classes.
Oh, you wrote it in the photo?
I think it was the module
3.
3, if I'm
Okay.
not wrong. Yeah.
Okay. Okay. What would be the first class interval for the frequency histogram? Okay, I have to look at it. So let me. Okay, so I'll just show everybody here. This is the question. Yours for you it was 13, but it randomizes the selections. Yeah, it's going to be different for everyone. So I have to look for this one with the frequency histogram. Okay. I don't want to show you all the answers, so I'm turning it off. I can see preview. All right, here we go. Histogram. Okay, this is it. And you wrote, you got 5 to 6. Okay. Okay, CFO is looking at what percentage of a company's resources are spent on computing. He samples, so you see why I didn't do this in class because it's already 20 minutes. 20 minutes. He samples companies in the pharmaceutical industry and develops the following stem and leaf display. What would be the first class interval for the frequency histogram? Oh. What would be the first class interval for the frequency histogram? Oh, because it's probably using, look at this. They have like a formula that they're using. That's why. So there are 50 data measurements, 2K, where K is the number of classes and 2K is the closest value larger than 50. So this whole thing is described probably in the book that I don't get into details, but you need to go in the book and see that. Is that what you did? Did you use the formula in the book? Or you just misunderstood the question?
I
Because
was looking at the book, but I didn't. Yeah.
okay, because they're going from they're taking the data from here, but they're going to make a histogram now, and there's some rules about how to make a histogram. And the reason why I don't get into all those details is because from book to book or professor to professor, they're going to do it different ways. And I just, just follow the instructions of the book and you'll get it correct. But the instructions are here.
Okay.
Okay. So check that out. Okay.
Okay.
Is that what you did?
Yeah.
Is that what you did though?
No, I haven't checked.
Okay. Check the instructions
I
of how to
checked-
make a histogram and then it'll be fine. The rules will be there. Pretty sure. If I go
All
here.
righty then.
Yeah, let me see here. Just to scatter plots. I have some sort of rule there in my notes too, but again, when it's not standardized, I don't get into too much details because it'll be just that you have to follow the directions, That's basically what you have to do. So here they have frequency, Pareto. Where's the histogram? Sometimes when they modify textbooks, they make errors and they have like instructions and then they delete the instructions, but then still use the same questions. That's when you have problems, when textbooks have different, specific instructions that are gone. But it looks like, I don't know, I don't see the relative frequency histogram, frequency distribution. See the next page. Histograms, okay. See? This is what you're going to read.
Okay. On the table.
Follow the steps.
Okay.
But in general, I'll give you the instructions, or a book will give you the instructions how to do it to get it precisely, but it's probably it's not a big deal until you have to decide if you do it different ways. If you were to make a histogram of data with different intervals, basically,
Mhm.
again, like we talked about the stem and leaf,
Mhm.
if they look different in terms of the 5 features, you have to make a decision which one you're going to pick. And you should base it on the one that corresponds to the best story you can tell, the most realistic story you can tell. But yeah, this is just an exercise. Follow the directions and let me know if it doesn't make sense. Okay.
Will do.
Okay.
Alrighty.
Okay. I think that's it. And now you know why I don't do that in the class, because it's 20 minutes and we have better things to do in the class time. All right. So I'm glad I could just put this video here for people who want to follow up about the Connect. And yeah, get 100% on your Connect. Try as many times as you can. And I've opened it so you should be able to see now your results. If you had 100%, you should be able to see the quiz and study from it. All right, bye. See you guys next week. Let me know if you have any questions or you need to meet with me. I'm available. I can make myself available. Ciao for now.